Let's now start with arrays, and then I'm going to summarize about the basic operations about arrays that you should know, and then we'll consider just one simple example which you may not have seen earlier. Okay. Array is simply a sequence of index elements. Remember, indices actually start with 0 until a.length minus 1, for example. And the size of an array is really fixed at the time of its construction. That's really kind of the drawback, the inflexibility of using arrays, which we'll address it completely using a linked list. That's something, point number 1, you want to make a note. And that's just one example. You have to specify the precise, the exact size, like how much memory the compiler should really allocate for this particular array. However, it's a heads up. Not really to be covered in lecture number 2, but later on we're going to talk about, in order to really address this particular fixed size inflexibility limitation for arrays, we're going to talk about some resizing strategy. Of course, that'll be the overhead of the arrays. In the case of linked list, you don't really have to worry about resizing. Okay, and we're going to talk about 2 flavors of a resizing: increments versus doubling. And how do you choose one over the other? Well, you have to do some rigorous, exciting mathematical analysis to really judge, right? That's something I'll definitely cover later, maybe in lecture number 3, okay, when we move on to the next topic. But just as a heads up. And let's talk about the supported operations on an array, right? You should know all of them already, but I'm going to talk about some extra example at the end. Accessing the array we talk about is going to be array indexing will just be constant time operation, right? Big O of 1. Easy. And what about updating a particular cell of the array? Well, assuming that I here is actually valid index, in that case, you want to assign that into some expression, right? So the updating itself is just indexing, basically, and then change the value in that particular index. So that'll be also a constant time operation, right? What about inserting and removing, right? Let's say, well, just in general, if I got an array of size 10 and I have already filled up all the elements in the array, well, it doesn't really matter, but let's say we already filled up. That's easier for you to visualize. I already filled up all the 10 elements, and now I want to insert an 11th element into the array. Think about what will be the step that will be involved to insert this particular new element, maybe at the end. In that case, it will involve you creating a new array with a strictly larger size, and then you have to copy over all the old elements into the new array, and that copy itself will definitely require some loop, and the loop's running time will correspond to how long the existing array is, which will be more like a linear time operation, right? It sounds like that's a very informal recap of what I'm gonna talk about more precisely, right? Let me use this particular example over here, example code, to really illustrate inserting and removing in the array. Typically, is not a very good idea because they're expensive, right? If you look at the structure for the code, oh, by the way, I'm only showing to you inserting over here, and it would be your optional exercise, definitely, to think about removing. Let's say I want to remove a particular element in the array, particular index position in the array, and then make sure there's no gap of null references in the middle, right? That's something I'll let you do. If you only take a look at this particular fragment of code, and remember at the end of lecture number 1, we did a series of derivation of the asymptotic upper bound for Java code. Without understanding exactly what this fragment of code is really trying to do, if you only look at them, you can see we got one loop over here, we got another loop over here. It looks like it would be a linear time operation, looks like. Right? But of course, we cannot just assume it's going to be the case. We have to do some rigorous analysis. That's something we're going to do when I illustrate. But anyway, and I just omit throughout the course. Sometimes you might see I omit the curly brackets over here for method just to save some space and for my job for my presentation. But from the indentation, you should know exactly what the program really means. Of course, I wouldn't typically give you the source code which I discussed in the class, some of them. In that case, it will be up to you to really code them up in your Eclipse and then play with them yourself, right? That's something I rely on you. You are in the second year, you don't really need me to spoon feed you for that, right? I'll spoon feed you for other things. All right, so eventually we'll see that the complexity for inserting or removing both of them, each one of them will be just a linear time operation, right? So that means it's going to be proportionate to the size of the array, which in some way is not good if you compare with constant. Constant is definitely, as I said before, ideal. But if you go to linear, then it's definitely worse than constant, right? Linear time operation. All right, let's now take a look at this particular fragment of code and study that carefully. Okay, and this is the fragment of code over here. All right, let's now talk about the input parameter first. So here, the return type is simply just going to be another string array. So getting a string array, we want to return another string array, input and also output. Okay, and the size of the array is going to be just n, right? It's the same convention. You can assume that n is always going to be a.length. And then this will be some string value that we want to insert into the input array, into some valid index. You can assume that I over here, that's the assumption we make. Okay, you can assume that I is actually going to be between 0 and also a.length minus 1. Right? That's something you can assume. All right. And then if you look at the body of the code over here, let's now take a look. Why don't we just do some example illustration that'll be much easier for you to understand. All right. Let's say we got the input array over here. We got Alan, Mark, and Tom, an array of size 3. So that's why we pass 3 as the second arguments. And then we want to insert Jim, the fourth person, into index 1. That's what we want to do. All right. And you can think about this part over here is A, and this is N, and this is string E, and this is index I, right? You can see the correspondence. These 4 parameters, which will be manipulated in the body of the code, they simply correspond to these 4 particular values, which I'm going to illustrate over here. All right, hopefully that's clear to you. Let's now start with the input. Let's say this is how we start with the input array A, which will be containing Alan, Mark, and Tom. And I'm not going to put the names into the quotes, but you can see what I'm doing here for illustration. So it's going to be Alan, Mark, and Tom over here. Eventually, what we want to have is we want to insert Jim into position 1. However, it will be wrong to simply replace Mark just by Jim. It will be the wrong way to go because now you're sacrificing Mark, right? So that's not the way to go. The way to go, let me just talk about it briefly and then we'll see how exactly to achieve it. If you want to insert Jim into index 1, right? What you're going to do is, before you can do that, you want to shift every element that's already stored at this particular index to be inserted, which is I. You want to shift them to the right by 1 position. So Mark should be shifted to here and Tom should be shifted to here. That's what you're going to do conceptually. And then, so this part over here will be left empty. In that case, you can put Jim in. That will be the conceptual idea. But let's see exactly how to achieve it. Okay. So let's now start with this part here. First of all, you can see this part here. We have to have a new array over here. So this line here. So the result is going to be a new array that we create. And since we are inserting a new elements into the array, so the size should be strictly larger. So that means we got n plus 1, right? And so this is exactly what we're doing, right? You can see size 3 and size 4. Initially, all these cells over here are storing just null. Okay, let's talk about running time right away, shall we? And what will be the running time just for this particular line over here? Well, this line over here will just be bigger of 1. Creating a new array, creating a new object just to allocate the address for the array. So that one is really a constant time operation. You can see this is just arithmetic and some assignments, and yeah, that's just big O of 1, right? Big O of 1. It's really important to see this. And then we're going to look at the first loop. The first loop over here, let me use green. The first loop over here, let's take a look. This one here. Okay, this loop over here, let's see exactly how we can do it. We got loop index j over here. J will go from 0 until I minus 1, right? And what's really I minus 1? I minus 1, I is actually over here, right? And then I minus 1 in this particular example would be 0, right? So we go from 0 to 0, just 0 over here. And then we are simply just going to result j is assigned to aj. So what we're doing this is, we know that eventually Jim will be inserted into index 1. So everyone to the left of Jim should be just copied over verbatim to the array in the same position. Let me emphasize again. So what we're going to do is, in this part here, we're just going to say result, for example, result 0, right? State j start to be 0, and it's only going to be 0 because here it will be just 0, the maximum value you can take. It's assigned to a0. Right? So what we do is result at index 0 is going to store the address of whatever address that's stored in index 0 of A, right? That's some basics you should have known already, how to understand this from 2030 or the earlier course. All right. So what this will do is it's going to copy over Alan to this one here, Alan. And I want to emphasize something over here. Notice that the index over here, whatever we pass j over here in the result, is copying from the same index over here. It's really important to note. Okay, simply just here. Right. So this one here doesn't. This part here doesn't really mean like a pointer. This is just to say copy here to here. All right. That's number one. Step number. What will be the running time for this? Okay. The running time for this is It depends on how large I is. Right. It really depends on how large I is. In that case, well, I could be, for example, well, this will also give us some hints, right? The initial assumption over here. A dot length we know is actually n, right? That's what we assume to be n. So the more mathematical, well, we talk about worst case. So I minus 1, we know I, the maximum value for I will just be n minus 1, right? So that will be big O of, in this case, I, the maximum value could be n minus 1, and then minus 1. Let me say it again, just to make sure you really got it, right? We go from 0 until I minus 1, right? Starting from 0 until I minus 1. And the largest value I can take, according to our assumption, is a dot length, which is n minus 1, right? And we go from 0 until I minus 1, right? How many numbers do we have? So we're talking about this interval from 0 until I minus 1 inclusive, right? As we discussed in the earlier part, there's a formula is going to be I minus 1 minus 0 plus 1, which will be just I. And we know the maximum value for I will just be n minus 1. So it's going to be big O of n minus 1, which will be just big O of n. This loop over here, right? We're talking about the worst case. And we'll do similar analysis for the second loop in a moment. Okay, so far so good. And let's now talk about the next line. What about this one here? This one here, just to insert the intended element into the intended index. Okay, so what we're going to do is we're going to use orange over here. So I over here in our example is simply, again, remember it's just 1. So we're going to do result at index 1 is assigned to E. In this case, E will just be Jin. That's what we're doing, right? So that means Jin is actually going to be copied over to index 1. That's what we're doing. And what will be the running time for this? This one should be straightforward. Array indexing and also variable assignments, right, is constant. So big O of 1. So far so good. So far we have done the analysis and also visualization for line number 1, 2, and 3. We got 2 more lines to go. Okay. What about this loop over here? Okay, this loop pretty much similar to the green one that we highlighted, but there will be some trick about the indices, but it's pretty easy. Not bad. Let me walk you through. So this part here, let me highlight it in pink over here. Okay, this part over here. Let's talk about the starting value over here. J, the loop counter, is going to start with I plus 1 over here. Wait, right? We're going to go from I plus 1 until n minus 1 inclusive. So we're talking about the interval over here. Let's talk about interval, which will be go from I plus 1 to n minus 1, right? You can see it's less than or equal to, right? So how many numbers are in between? Well, let's apply the formula. N minus 1 minus I plus 1 and then plus 1, which will be, let's now simplify that, it's going to be n minus I minus 1 plus 1 cancel out and then plus 1, right? So this will be the number of iteration that we have, right? That's what you're going to have. And here, remember, we talk about the assumption on I, right? So if you look at the I over here, what's the minimum value for I? The minimum value for I is going to be 0, right? Well, just be careful. You can rewind the video. When we talk about analysis for this one here, we're going to consider the maximum value for I. But now when we talk about the I over here, we're going to consider it's a theoretical minimum over here, which can be the minimum index. And so, which will be worst case is, let me just use the same pink value so you will see I'm talking about the same line of thought. So that means it would be n plus 1 when I is equal to 0, right? You might be wondering about why the maximum number of iterations for this particular loop over here after our calculation is going to be n plus 1. N is the number of elements in the array. How can we actually run the number of iterations that's larger than its size? You're absolutely right. I made a mistake in calculation. Maybe you already noticed that about a few minutes ago. Let me fix that right away. I just noticed that. Okay, so when I try to simplify this particular calculation over here, it should be n minus I minus 1. All right, you can see n minus 1 minus 1 minus 2 plus 1 should be minus 1. Okay, I just make a mistake, right? It's embarrassing, but I'm willing to fix it. It will be n minus I minus 1. All right, now make perfect sense. But asymptotically, it wouldn't make a difference, right? As I said earlier in the module, whenever you're asked to, not in the earlier module, I mean the earlier part of this module, whenever you're asked to approximate the running time, it would be okay to, there will be some tolerance on some minor mistake, as long as that minor mistake does not really impact the resulting highest power of your formula, as long as it's not the case. Otherwise, if you only make some mistake on the lower term or lower power or multiplicative constant or lower term, that will be okay, right? If when your goal is to approximate. Anyway, enough about excuses for my mistake. So it should be n minus 1. All right, n minus 1 when n is equal to 0. So that means this will be the maximum number of iteration for that second loop. This will be the maximum number of iterations. All right, that's good. All is good. And then if you look at, well, in this case, we're talking about running time first before we trace the code. We haven't done this part yet, but we will. And if you look at the body of the loop for every iteration, if you only look at that without knowing exactly what it is supposed to do, let's do the running time analysis first. This will be arithmetic and then array indexing. Okay, so let me just arithmetic, array indexing, variable assignments, and also array indexing, right? All of them are simply just constant time operation. So overall, it's going to be the maximum number of iteration n minus 1. So you'll be big O of n minus 1 multiplied by some constant, which will be just n minus 1, right? So that will be just big O of n. Right? Let me make a note over here. So far we have got the running time for this, and also this. We still got the final line, which is trivial, but we'll get there. Let's now trace this loop very quickly. This loop is supposed to go like this. So again, this loop over here. So we start with I plus 1. I in our case is actually 1. So we'll start with index 2 plus 1, right? So go from there, and then we're going to go all the way until n minus 1, the last index, basically. And I just noticed another typo on my code over here. Let me point out to you, okay, and do the corresponding fixes. Here, I'm saying that the last index is actually n minus 1. That's actually not true, because remember, n is actually 3. 3 minus 1 will be 2. 2 indeed is the last index for the original array, but for the resize array, it's actually not 2 anymore, right? It's being incremented by 1 by its size. So what I really meant to say, there are two ways for you to fix this. I'll fix the slides as well when you download it. either I can get rid of this just to say it's exactly just n. So n is the old size of the array 3, which would be exactly just the largest index for the new array. That's one way to fix it. Or over here, you can simply say a.length minus 1, because a is or over here you can say result.length minus 1. That's another way, but I think n would be better. All right, and let me fix our analysis earlier quickly. Okay, you wouldn't change the calculated result, but the intermediate detail need to be fixed quickly. So here, rather than n minus 1, right, it's now going to be n over here. And of course, it's going to be n over here. Okay, so let's see. n minus I minus 1 plus 1. So that means just n minus I. Minus 1 and plus 1 cancel out. So it would just be n minus I. So we don't have this minus 1 over here. Okay, so it will be just n when I is equal to 0. So that'll be the maximum number of iterations over here, right? That's what we got. All right. Okay, and that's let's now try to trace the code. So we want to go from index I plus 1, which will be 2, as I explained, all the way to the last index. In this case, it will be exactly n, which will be 3. All right. Let's now try to see how this will work. And notice that here we got result j. For example, j over here is assigned to aj minus 1. So this will be assigned to mark over here. And 3 will be assigned to index 2. That makes sense because since we already insert Jim into index 1, and starting from what used to be an index 1 over here, which will be mark, we want to shift them to the right by 1 position. That's exactly what's happening over here. Right? So if you want to have a little bit more concrete explanation, think about this. In this particular example, we're going to say result of index 2. Over here, we'll copy whatever that's from index 1 from the original array A. It's assigned to A 2 minus 1 over here. And then result at index 3 over here, which will be the last index. Index 3 will be assigned to A 3 minus 1, which will be 2. And we're going to copy this over here, right? That's exactly what's going to happen for each iteration. So we copy Mark over here, and we copy Tom over here. All right, so that's about the tracing for the second loop. And finally, we want to look at this final line, return. That's outside the loop, so it's going to be big O of 1. So now we got how many lines have we analyzed? So we have analyzed this, and this. So the ultimate running time goes like this. Okay, the ultimate running time goes like big O of 1 plus n plus 1 plus n plus 1. Okay, if you want to include all of them, which will be big O of n. Right? So you can see 1, n, 1, n, and also 1. Right? And then you can make 2n plus 3, which will be n, asymptotically. So that will be the overall result for this algorithm for inserting an element in the middle of the array. Right? And again, notice that there's a typo over here. I'll fix it in the slides and make sure you understand the calculation over here. That'll be important. All right, let's now go back to the slides. Right, so this slide here basically concludes about what we want to discuss about the primitive operation or basic operations on the array. And you should really know that inserting and similarly removing are both expensive. They will be linear time operation. All right, let's now try to do some case studies on the arrays.